For joining. I'm Paul Menzel, and I'm talking about booting fast. Why does power on to log in still last longer than 1 second? First, thank you for all the organizers. It's a great event. I'm looking forward to the evening, and it's great to talk to you all here in the breaks and so on. Some words about myself. I'm a free software enthusiast, and my day job is at the Max Planck Institute for Molecular Genetics. We have 2 server rooms with 200 servers, more or less, also some of the newer ones, so 256 threads and 1 terabyte of RAM. Maybe for some of you that's not much, maybe for others it is. I'm interested in core boot, the Linux kernel, and my pet peeve is trying to boot as fast as possible. So, so why is it taking so long? What do you think? I think we can make a test. So maybe everybody of you shuts down their phones and then starts it again, and the one who is first says something and gets a something. Or with the TV and so on. The thing is, the answer is nobody demands it, right? It's on the priority list for everybody. It's not very high. It's more important for some of us to have the fastest processor, the biggest amount of RAM, the best display, and unfortunately there's no such device either in server space, in desktop, laptop, or mobile phone space where this is possible. But on the other hand is so actually that's the answer of the question, and I'm done. So. But let's see where we are at a little bit, and maybe some things we can do. I'm not that much of a hacker. I'm just know about the workarounds maybe, and maybe see some points where improvements could be made. But unfortunately, I'm dependent on others there too. So if you compare from some years ago, a Chromebook, for example, the first Chromebooks, they booted in 8 seconds, from pushing the power on button to log in screen, which is pretty fast. But on the other hand, if you nowadays also look at the Windows 11 system and seeing booting it up, it's also quite fast. It's in 11 seconds on a traditional standard Windows laptop. There are some videos on this on the net, and ChromeOS in this case took 15 seconds, but the reason is it had to do memory training. So there are several components involved in booting fast, and one of it is the firmware, and memory training takes a lot of time. So a lot of solutions for this problem is caching, right? You do it once and then you cache the memory training data, and then the next time it is much faster. On a newer Chromebook, I asked in the IRC channel yesterday, Coolstar and Mr. Chromebox did some tests on AMD devices, and so on Chromebooks you can also run EDK firmware and Windows to a certain extent. There are some audio driver problems which are fixed by Coolstar, I think now. So it took around 8 seconds. But I also have ARM Chromebooks where it takes longer, unfortunately. But firmware is an important part, and there with core boot-based firmware, which is used by the Chromebooks, for example, or System 76, and maybe some hyperscalers now. Besides that the variable is obviously not initialized, the zero boots stamp, there you can actually see where time is spent, right? And and sometimes you see that it calls into some platform initialization code, FSP, which also AMD and this and the interface also AMD adopted, and there we don't have any insight, but it takes 300 milliseconds, 140 milliseconds. So in the end, when on this Chromebook, the actual operating system kernel is started is after 1.2 seconds, but 5 or 15 years ago on Intel devices, it was after 300 milliseconds. Yeah, so there's also a lot of verification stuff done in here. It also depends on how much the payload is and so on. But let's say the Chrome folks actually they want to try to get below 1 second. Yeah, but there's already 1 second spent. So time from power on to login screen is you have 0 milliseconds left to do anything else. So with this firmware situation, it's quite hard. Then we have the bootloader, and there with UEFI on the traditional legacy UEFI systems, you have a boot manager with the ESP partition, and actually instead of loading grub, or I haven't measured system deboot, for example, but with the AFI stub support in the Linux kernel, it pretends to be a PE executable, which can be run by the firmware. So you can nowadays cut out the bootloader already because it's shipped in UEFI. That everybody can set this up. I know. Has anybody know? Does somebody know how many milliseconds system deboot maybe needs? Okay, thank you. Yeah, then I have an older system, and maybe 10 years old, in old AMD A84 chipset, and then I do some tests on it, and my current situation in there is, which is probably long or not, that systemd analyzes show after it's also supported by coreboot. So after this 1 second, the Linux kernel says it takes around 600 milliseconds, and then the user space, it's an SSD, not an NVMe. It takes 1.6 seconds according to systemd analyze. It doesn't mean that there is some login screen yet or so. Yeah, but that's one thing you can use systemd analyze. It's thanks for all the authors. It's a very nice tool to use. There, of course, it's also nice that the Linux kernel shows the messages with the timestamps in a very high precision resolution. Yeah, first, sorry, my pandoc foo is not so good, but I think the most important stuff can be seen here. And I also was actually quite okay with the layout because Leonard in the past also used the Beamer style, but today I was, I saw that I have to step up, and next year hopefully it will be a better layout. PowerPoint. Oh, okay. Yeah, so yeah, the next thing is often the distribution kernels, they want to support a lot of systems. So to boot fast, you actually probably are not able to get around not building your own Linux kernel, optimized for your system, which is, there are also some tools, make local dev config, for example, which sees which modules or which components are loaded. And then the biggest advantage is first, it's of course smaller, so you have less to load and less to execute. And and often in the distribution kernels, a lot of stuff is probably also executed in the beginning, or at least probed, which you also don't need. But what I wanted to get in here is that first you have to see what you actually want to measure, right? So what I often do is look at when is the init process run, this timestamp, and maybe also when the first systemd log message appears, which is here, but systemd already executed beforehand. So here in the systemd analyze output, you see after 596 milliseconds says the kernel is finished. So you see, that there is 200 milliseconds spent in there between the kernel hands off.
Just a quick note, you can't compare these times because this is clock boot time and the other one is clock monotonic.
Sorry?
So it's a bit icky comparing these times because one is clock boot time and one is clock monotonic, and I always assumed they would start at the same moment, but they actually don't. So, it's not that you can't compare that. There might be multiple tens of milliseconds difference between the two.
Ah, okay. Good. Yeah, then I have to look more into this. Yeah, thanks for the insight. Yeah, but yeah, the Linux kernel timestamps, I think they're also a good way to look into how much you improve or not. Should I put it? Yeah. All right. So some things you maybe can do right away. If you look at some of the timestamps, there's this init called debug kernel command line option, which you can use, and where it says how much all the init functions of the Linux kernel took to execute. And one of the things you see is that, for example, for the crypto stuff, the Linux kernel runs some kind of tests in the beginning at each boot, right? And you can disable those. I think it saved like 200 milliseconds of the boot time on my system. And you can blacklist if you don't want to build, if you want to use the distribution kernel, you can also blacklist certain init functions. Yeah? And that's with the init core blacklist keyword on the Linux kernel command line, and then you can also use this. One thing I noticed which is unfortunately was there for a long time, when I saw, okay, it detects my hard drive, and why does it take so long? With the SATA connection as a HCI protocol. And then it turned out that, I don't know, 20 years ago, I actually had to look in the, it actually was added before Linux converted from BitKeeper to Git. It was that old. At least I had to look in the historic archive, yeah, and there was a 200 milliseconds delay added, yeah, and then everybody else, yeah, used it too. So I mean, now SATA is probably old, and everybody uses NVMe, and maybe so. A lot of million devices, yeah, each boot wasted 200 milliseconds because some hardware back then had some chip bug, and the developer back then said, okay, 200 milliseconds delay is the solution. And there was one commit which disabled it for one specific device. And I was in contact then with Damien Lemol, the maintainer of SATA, and he, yeah, I mean, there's a no regression policy, right? And there are a lot of hardware, SATA controllers and hard disks. And now the question is, can you revert this delay, and how can you best do it? The status quo currently is that there is a new no debounce delay parameter, which you can apply to all the ports of the SATA. Yeah, of the subsystem, libATA, and there you can disable it, but of course it's only then happening for those people actively doing something. Yeah? So all those people with standard distributions and so on, they still cannot profit, right? So they still have this delay. So there is a question why, how maybe this can be remedied. I have to put it back on the agenda. And then the next thing is, if you, the ATA driver, they had a debug a macro defined, and if you enabled it, you could also look in what parts the code took a lot of time. That's the first thing. The other thing is the ftrace. We will also come back to it. And you can see that there are also some debounce timing stuff, and the defaults are 5 milliseconds, 100 milliseconds, and then 2 seconds timeout. And if you decrease it manually to 1 second and 5 milliseconds, for example, at least it worked on my systems where I tried it, and it also cut off 100 milliseconds.
165 milliseconds.
165. Okay. Yeah. He said how much time system deboot took, and it's 165 milliseconds. Thank you. So if you load the Linux stuff directly, then you save this time. Yeah. So, I mean, we always have to think about if the goal is 1 second, yeah, then 165 milliseconds is already it's already 20%, right? So that's then a long time. Yeah, so this is my latest experience with the Linux kernel. That actually, I would say there should be a rule for the Linux kernel. Every sleep time, which is longer than 1 millisecond, has to have a comment and be justified to be added. For example, yeah, some data sheet or hardware bug or whatever. But I think that's just a dream of mine. Yeah, then there's also going on some work, of course, from different folks. Yeah, the Chromium folks, they also do some boot time analysis. There is this probe prefer asynchronous flag, which you can apply to a lot of subsystems and then or init calls, and then it's going right back and says, okay, it's finalized, and actually doing it in parallel. And if you test a lot of stuff, and then that's a good thing, because today we have a lot of cores and can optimize the boot time by parallelizing certain things. All right, yeah, so that's the flag below there, the probe type. But sometimes, I think I once tried it for the Intel Linux kernel driver, and then it didn't work in some situations. Then there was some problems with the sound system, and now I think they fixed it, and now they enabled it again. Yeah. The next thing, which takes a lot of time, is the Linux, the graphics drivers. There, the solution is it depends on your use case, that you can use the frame buffer, and then, for example, Weston, the window manager, Wayland has some thing that it can migrate seamlessly from the frame buffer to when the other DRM subsystem is initialized, and then you can use the accelerated capabilities. That's a thing, but yeah, they also don't look for optimization, and if you later load the Mesa library, it also takes a lot of time because it's so big. Yeah. So that's the thing. Then for servers, there's also a problem. That at work there was a PowerEdge server, AMD, which where the Linux kernel takes 17 seconds, right? And that's, I mean, the long boot time, it has a downside. Nowadays you want to use you want to restart often, right, to apply security updates and so on, whatever. And then sometimes, of course, the firmware also plays a role in servers. If it takes like 10 minutes or so, yeah, then you say, okay, I don't want to restart the users, they need the service and so on. So that's a big problem also when boot times are so long. It prevents, I think, people to run an up-to-date software stack. But for the servers, because of a lot of PCI devices and a lot of threads, you always you also see where a lot of time is spent. And the one thing is ACPI and PCI subsystem. I think Windows, I mean, not on servers, but on desktops, they already have this fast boot modes. They also cache certain stuff of this. And then here, I think it's now worked on. The microcode updates, they are applied serially. And for 256 threads, it takes 2 seconds, right? So to apply these microcodes. Yeah? So these are also things which is also Amazon be made aware of, and they had a parallel CPU bring up patch. And after a lot of discussion, and I also asked them what the state was, Thomas Gleixner from Intel actually tried to improve a lot of these boot paths, and they, I think it's not really parallel because that's not possible due to the architecture design, but it brought it down quite a lot, and this 6.6 series is also on the microcode parallelization stuff. All right, now to user space. Then next to systemd, above it's systemd analyze. So next, systemd analyze has also the command critical chain, which gives you a rough overview where probably most of the time is spent, but it's not 100% correct, and you should use the boot graph or systemd boot chart programs. And what I found out on this ASUS system is that here in the past, for example, the systemd time sync D stuff is, is taking a lot of time, and actually was true also when I looked at it with systemd bootchart. And the thing is that systemd time sync D now has all these lockdown features, so that it has a private environment somehow, and is encapsulated, yeah, or what systemd provides. And actually looking at this, that's actually all these calls take 10 milliseconds or so, yeah, on the system. And then it's actually adding up where you think, okay, it's actually a small program which runs. It's actually these security features in this case also has a boot impact. In this case, I also had to think about, okay, time syncing. This is a desktop system, not a server, no network file system, whatever. I then took the system time sync D stuff out of the sysinit dependency and ordered it differently. Yeah. So there's some things you can optimize, and yeah, due to the time, yeah, the systemd analyze also has the user stuff. So if you actually finally got into the GDM screen, if you are on a desktop, then I don't know, if you log in, it also takes, at least on my system, a lot of time. Yeah. So also in Genome also, starts a lot of services in the background, and at some of them you can look with also with systemd analyze critical chain, but a lot of those stuff is also in the user journal, and you can start a profiler next to it. Yeah, it's best then to have GDM running, for example, on a console. You start this prof, for example, and then you start profiling stuff. And there's one Genome developer who's now looking into this, and he uses GnomeOS, for example, and also wants to log in 1 second. And he already found certain stuff also in systemd and sent a patch, I think, last time on the mailing list. All right, yeah, then there's a fuzz argument, and yeah, which gives a little bit more context. And then, yeah, for the genome guy, that's, I think Christian is the name, Hegert, he has some blog post published recently where he says how to use this prof and go on there. So in the end, yeah, I think a lot of focus has to be put on boot time. In server space, stuff gets larger and therefore takes more time. So new concepts have to be thought about. Maybe also with caching, firmware is an important part. And yeah, maybe what I heard, I talked to some Amazon guy. He said actually they have an internal patch set of, I don't know, 12,000 patches or so for the Linux kernel. And they are actually down to booting the Linux kernel in 200 milliseconds or so, because whatever they could put back, they did. And the David Woodhouse, he actually upstreams a lot of stuff, but I think, yeah, it's so much patches. Let's hope they have more time to also upstream this stuff. Yeah, sorry it was a little bit run through in the end, but thanks for your attention, and maybe you have some questions. And 2 minutes, yeah.
For questions.
By the way, you maybe missed one area, and it's systemd itself. We actually find out if you will be hunting for every millisecond to actually look at generators, because quite of those you actually don't need on your system. Maybe migrate from FSTab to regular mountains. That will also save some time. And I think also it would help a lot to convince Lennart to actually move from unit files to database, like binary database to unit files, because reading unit files is really slow. Sorry, that was not a question.
We have like 15 seconds. Anybody have something fast?
Have you experimented with I/O speed versus CPU speed with compressions of initRD?
Yeah, compression of initRD, LZ4 is the best, because at least with my SSD loading, the more bigger archive is faster than the slightly and the smaller decompression speed then gives more boot time.
Do you know how slow it is to decompress Do you know how slow it is to decompress NRD? Like how much time is spent on that?
I think it was from 120 milliseconds to 40 milliseconds or so.
I mean, the reason is that I'm asking is because we have been thinking about doing something different there, with mounting like a file system right away from memory, so that we don't have to spend the time on actually unpacking CPIO into the tempfs, and instead just having something ready there. Then you save some time, and the decompression happens basically on access instead of ahead of time. So that might actually get you something.
Nice. All right, the other questions after this, but thank you all again and enjoy the conference.